One widespread application of linear approximations or differentials, again, those are synonyms for each other and for the same concept. Some people might talk about local linearity, others might say differentials, same thing. But one of the applications is to use those simplifications of a complicated function to derive error bounds for some output function. So the classic error calculations you see in chemistry and physics are often done using linear approximations to make the calculations easier and more general. So again, just reminding ourselves about the two-variable approximation. Change in f is approximately the x slope times delta x, y slope times delta y. If we're talking about the error, again, thinking here of, okay, so I measure x, I measure y, and I'm going to also have a true value for x and a true value for y that's slightly different from the measured values. That's going to cause a resulting change in our function. And we're curious about how large that function change could be, but we never really know what the error is going to be. What we're interested in that case is the maximum positive error in the function. So we slap some absolute values on this. And an important distinction here, we are going to take our derivatives, multiply it by the largest possible error that we could get in x, and add that to the absolute value of the maximum error we could get in delta y. And so this is really getting the worst case scenario. Typically, if you had errors in two variables, well, you might get one that's a little high or produces an overestimate, one that produces an underestimate of the function. But if we're interested in how bad it could be in the worst case, then we should take the largest possible error in x times its slope and take that absolute value. So that's one chunk of error we're going to get for sure, and add to it another positive quantity so there's never any cancellation. And that's going to give us a largest possible estimate of the error. It's pretty clear how this formula would generalize to functions of 3 or more variables. We just keep adding terms for each variable that's involved in the calculation. All right. So let's take a look at an example of a cylinder. So we've got a cylinder, it's got a radius of 2.5 centimeters. So r is 2.5. And the height is 15 centimeters. And we measure it on a scale and we get a measurement of 330 grams in terms of its mass. Typically, we would be able to report the accuracy of our measurements to within, okay, some tolerance. Here we're going to say plus or minus 0.1 centimeters for the measurements and plus or minus 2 grams for the weight or the mass measurement. Let's start off by calculating what we would do in a traditional problem. We've been given these three pieces of information and we calculate the density, say. Well, the density, of course, is mass over volume, and that's mass over pi r squared h, which is the volume of a cylinder. We've got 300 grams divided by pi times r squared times h, and we get approximately 1.018 grams per cubic centimeter. So that's something actually very close to water, in fact. Water is 1 gram per cubic centimeter. All right. And that doesn't sound right at all. Let me just double check that. So we've got 300 divided by, I guess we got the pi in there. Just surprised the denominator, yeah, okay. The denominator comes out to about 300 as well. So we get that measurement, or that resultant value. We didn't actually measure that, we measured the inputs to it. And of course, if there was some error in our inputs, there's going to be a consequent error in our calculated value. Let's take a look or use that error formula we introduced earlier to calculate the error bounds for that measurement. So we have density is 1.018 plus or minus something. All right, well, let's take a look back to our density calculation. Let's just call it big D. If that's our calculation that we performed, we can immediately go to the differential, or we're going to use the approximation formula. Actually, let's go straight to the max D error here. the worst case for the error is that it's going to be less than, there's not really absolute values there either, the error is going to be less than the absolute value of the derivative of the density with respect to mass times the mass error, the maximum mass error, plus the absolute value of the density's derivative with respect to r times the max r error, plus the absolute value of the density differentiated with respect to h times the maximum error in the measurement of the height. We already know a couple of these things. We've been told, oh yeah, this is plus or minus 2 grams, so the max mass error is going to be 2 grams. Again, we just take the positive one. We're going to take absolute values before we're done anyway, so we might as well take the positive as the largest value. Likewise, these two values here, the maximum error we would accept, or that we believe is in our measurements, is 0.1 centimeters or 1 millimeter in both the radius and the height measurements. All right, so we have these three values already. They've been given in the problem. Now we're interested in calculating the rates or the effects of each of those on the density calculation. All right, let's start off with the mass. It's the easiest one, in fact. Remembering we treat everything else as constant, mass derivative with respect to mass is just going to be 1 times the constant in the denominator. The h derivative, let's do r next. The r derivative is going to be this is r to the negative 2. So we'll have negative pi r cubed, sorry, negative 2 pi r cubed h. We bring the negative 2 out front and get a negative 3. Last but not least, the height differential, height derivative. We have h in the denominator, so h to the negative 1. We'd have negative m pi r squared h squared. And notice a few things here. These two negative signs are telling us that if the radius were to increase, well, our density would decrease if all else was kept constant. If we had a fixed mass and we just made this thing larger, then our density would decrease. And same thing for the height. Whereas if we increase the mass, we would increase the density if we kept the radius and the height the same. So that's our flashback to the interpretation of derivatives. Now, to complete this formula, of course, though, we already know some measurements that we use. So these derivatives here should be used at the point that we considered, which was 300 for m and 2.5 for r, and h was 15. And if that's the case, then d sub m is 1 over pi times 2.5 squared times 15. dr is minus 2 times 300 over pi times 2.5 cubed times 15. And the height derivative is minus 300 over pi 2.5 squared and 15 all squared. We simplify those. And we produce these values for the derivatives. Last but not least, we include those in our calculations for the maximum error, and it's bound the worst possible case for the error given the possible errors in the input values for our density calculation. And I want you to notice again that we're putting absolute value signs around everything. So whether the change based on an increase in mass would be positive or negative as it was with radius and height, we're going to get rid of that sign with the absolute values. So this calculation here is going to be equal to, let's put this out, 0.003395 times the maximum error in mass, which is 2 grams. And we'll keep the negatives in, knowing that they're going to disappear shortly. Maximum error there was 0.1. And last but not least, we get that error due to the possible difference or error in the height. And simplifying, we get a maximum error of 0.09 grams per centimeter cubed. So let's fill that in up here. 0.096, that's about all we need given the precision of our density calculation. And so we can see that our average density around water is actually not bad, but there's a fairly significant error here of close to 9% on that measurement. And the errors that we have are fairly small. We should notice that, like 2 out of 300 is fairly small, 0.1 out of 2.5s, that's a bit bigger, and 0.1 out of 15 is not that big either, it's less than 10% anyway. But when we combine the possible effects of all three of those ganging up together in the appropriate way, the error could be as large as 0.096 overall. Now, that's a specific example. Some of you have also seen error calculations where we talk about percentage errors. And the way we could look at that using our new ideas of maximum error and derivatives is by studying this classic model of powers of the input functions. And again, some of you might have seen this. If you haven't seen this formula before, that's totally fine. But what we're going to do is just derive it anyway, because it's a straightforward application of our linear approximations or differentials. So the idea first is to talk about a relative error. If we've got an absolute error of delta A, the relative error is that amount over the actual amount. And sometimes it'll be converted to a percentage if we multiply it by 100. All right, so what we're going to look at in this example is a very general form. In fact, the previous example had this form, but with a constant out front, which turns out not to have any effect in the final analysis. It just gets carried around everywhere. This was basically the form we had in our last one. It's very common, just powers, positive or negative or half powers, can be anything, of three variables multiplied together. If that's our formula, then we can talk about the partial derivatives and, oops, getting ahead of myself there. How would we go about calculating that? We'd find the partial derivatives, mx to the m minus 1, y to the n, z to the p. The y derivative would be the x stays the same, the y gets brought down and reduced by 1 in power, and the z stays the same. The z derivative, x and y are constants, and we bring down the p power to get p negative 1. Those would be our three derivatives. Now, using our error formula before, our max error in delta f is less than or equal to, let's put absolute values on that, sure. It's going to be less than or equal to f sub x times delta x plus f sub y times delta y plus f sub z times delta z. Absolute values to make this always larger than the value we're talking here. All right, if that's the case, then that's definitely true. That's true from our general error statement before about linearization. Now, how does that play a role, or how can we turn this formula into the formula we have up here? Well, let's keep that the same here, maximum error in f, and let's put all the terms that we had in front. So f sub x is m, x to the m minus 1, y to the m, z to the p, plus, this time I'm going to bring the n out front, n, y, x to the m, y to the n minus 1, I get my powers right here, yeah, n minus 1, that should be an n up here then, and z to the p, and sorry, last one thing on the end, there we go, times, that's fx, times delta x, times delta x. And last but not least, the p, x to the m, y to the n, and one lower power of p times delta z, oh, for Pete's sake. There we go. So we had that as our statement involving the particular derivatives of f. Well, where does that get us in terms of this final relationship here? Well, if you look at all these terms, they basically have what f is. right? Except there's one lower power of x, one lower power of n, and one lower power of p. So what we slide in here is we divide this whole side by f, each term, and each term, and we divide the left-hand side to compensate. And, oh, I really just want to write it down. We could go to another page, but I think we can fit it in here. So this is delta f over f on the left, check. The right-hand side, if you think of one missing power of x and the y's and the z's as is, y's and z's as is, when we end up dividing, this term becomes m delta x, and there's one extra x in f, mth power, that is not in the numerator here, m minus 1th power. Likewise, this n out front here, the delta y we keep, but if we scan through, oh, we're missing one power of y that's in f, so we get delta y over y. And last but not least, p over delta z, p times delta z over z. And with those three terms, that's exactly what we have in this general formula. So that calculation leads to four simple functions like this, and one example would be m r squared h, something like that. That would fit this model here. We could jump directly to a statement about the relative error in the final output value by simply multiplying by the exponent of each term in its in the original function. So again, just a handy way to be able to apply linearizations to get, again, a simple formula. You could look at how these three things play out in terms of their effect on f, but it gets really complicated really quickly when you have the full function there. When you're talking about the linearized form, though, it's easy to say, okay, a little change in x gets scaled by m to change our output. Same thing for y and z. It becomes much more straightforward to assess the impact of small changes of the input variables on the output than it would be back with the original function. I wish we had time to demonstrate that, but we don't. So there we are. We'll leave that as a conclusion for this topic.